Recall back at the end of section 4.1 where we were talking about the natural exponential e raised to the power x and how maybe it's not obvious that that thing's natural. Well, its counterpart that we have in logarithms is also a thing that we call natural. We call it the natural exponential, where it is the logarithm base e, log base e of x, or the abbreviation that we generally use for it, which is ln of x, where ln comes from the mathematician Mercator in 1668, where it is an abbreviation of Logarithmus Naturalis, where I've also heard that called Logarithm Naturel for more French rather than Latin, but the point is there we're using that Latinized idea of adjective before noun, or adjective after noun. Yeah, adjective after noun, I had that backwards, but it's not natural for me to think in that way for the language, and it's probably not natural for you to think about why this ln is the really important one, but trust me, if you go very far in math at all, this thing is really, really, really important. It does some really cool things that, well, we're a little bit too early on to properly describe, to properly give context to. But perhaps we can think about this in that same way that we thought about exponents and compounding interest to get a little bit of a sense for why we care about this thing. We get a little bit of a sense for why we insist on calling it the natural one instead of anything else, like, say, the common logarithm. We like base 10, don't we? Why is this one better? Well, let's remember for ourselves that the natural exponential comes from the context of continuously compounding interest, that it will tell us the amount of money in an account left alone with continuously compounding interest rates over some amount of time t. This guy would do the opposite. It would say if you want to know how long it took to get that amount of money with a continuously compounding interest rate, whatever value that happens to be. We're going to see more properties of this stuff. We're going to see more properties of this guy and all of the other ones in our next few sections. So I'm not too worried if you're looking at this and wondering why we've decided this one's important. We haven't seen any of why it's really important just yet. We've only gotten some introduction to it, but trust me, you stick with this stuff and you'll learn about it. But for now, let's finish this section with a bit of an introduction through application for why we might care about the natural logarithm. When the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the function f of x equals 13.4 times the natural logarithm of x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 15 minutes. So we're getting an estimation here of what it looks like if you leave someone or something or some poor animal for that matter.
Inside the car, Sarasota County Animal Services recorded the temperature.
It was up to 115 inside the vehicle when she did the reading.
In a hot car in the parking lot. Which is to say it'll get very, at best, uncomfortable. Because what happens here for our function, based on the definition we have, is that after 15 minutes, we'll be looking at f of 15. That's 13.4 times the natural logarithm of 15 minus 11.6. Where that says here, what power of e would give you 15? Remember, e is about 2.7. So for something like that, we'd be looking for a value, let's say between 2 and 3, maybe 2 and 4 if we're being a little bit more open-minded there, but we're looking at something that's in that range multiplied by 13 minus 11. So if we're getting something between there, we should expect, as we'll see, to get an approximate value of 25 degrees, which is not to say that it's 25 degrees Fahrenheit in the car. That would be very cold. What we're saying instead is that the temperature would increase by about 25 degrees Fahrenheit in 15 minutes. That is, it would go from being somewhere between 72 and 96 to being somewhere between 97 and 121 degrees Fahrenheit, which is, suffice it to say, not survivable for very long and only going to get hotter. Here's one thing we can use the natural logarithm for, if not a very fun thing to think about. But hopefully at this point we've at least got some sense for why we might care about logarithms, what we can use them for, what they do in terms of exponentials. So we'll continue this on next week with more of an examination in what logarithms do, let's say, on their own terms. We're going to get a more detailed look at some of the algebraic properties that logarithms give rise to. See you in there.